Yesterday, I gave you a brief introduction to modern physics and most particularly special relativity. Today we are going to talk about the consequences of Einstein's proposal, right? This is consequences of special relativity. There are three that we are going to discuss. I think you will find that the overall conclusion combines all three thoughts together into one beautiful understanding of the universe. Special relativity, Einstein proposed two postulates. First postulate is that the relativity principle, which states that all physics apply in all inertial reference frames, is absolutely true. Postulate number two is that the speed of light is constant regardless of postulate number one, which is really what makes it special relativity, right? It's the fact that the speed of light is a constant value, whether or not you are in a moving frame or in a stationary frame, right? So the first consequence is illustrated in this manner. Keep in mind, each one of these was illustrated by Einstein by simply thinking about it, right? It's called thought experiments. I'm going to draw some pictures and help you think about it so we don't have to just use our imagination. But the first one involves two trains. Train number one, up here, started somewhere far, far away and is moving at a very high speed to the right, right? High speed meaning close to, but not at the speed of light, right? Very, very fast. This is called a relativistic speed because it is close to the speed of light. Train number two, stationary, right? Sitting there, parked, not moving at all, right? What we are going to assume, because we're using our brains to imagine this happening, is that train number one started over there, is moving extremely fast to the right, and just happens that at the exact moment where train number one is exactly lined up with train number two, right? At that exact moment, from the omniscient, which truly in true reference frames is not possible, from the God view, right, from us designing the problem, at the exact moment that train number one is in line with train number two, there are two lightning strikes, right? Lightning number one strikes right here, right? And number two strikes right there, right? So according to us, the designers of said problem, we see lightning happening at the ends of both trains at what we would call the exact same time. Make sense? All right, so running through train number one, or excuse me, train number two first, right? Train number two is not moving. So the light that propagates as a wave from this side propagates as a wave from this side in exactly the same fashion. The speed of the light, which we know is lowercase c, is the speed through which the light will propagate through the train, right? According to this, assuming that observer number two is standing in the middle of the train, seeing this happen, observer number two would say, those lightning strikes happened at the same time. Make sense? Should make sense. Equidistance apart, they did happen at the same time, therefore observer number two sees them as happening at the same time. Right, really not that weird of a thought. However, train number one is moving at a remarkably extreme speed this direction. So since the speed of light going this way is going to be c, not obeying the relativity principle, right? Then if we imagine that the train is moving at 200 million meters per second and the light is moving at 300 million meters per second, right? From this side, person number one, who is on the train and therefore also moving at 200 million meters per second, will arrive somewhere over here when this light ray propagates to them, right? Since the speed of light from behind is going to also be c, but during that time, observer one is moving away at an extreme speed, this light is going to take longer to eventually propagate to where observer 1 will be. So according to observer number 1, the lightning strike in front of the train happened first, then many moments later, the lightning strike at the rear of the train happened second. Everybody understand? All right. According to postulate number 1, the relativity principle, both people are correct. The relativity principle holds that in any reference frame, as long as you're moving at a constant speed, the laws of physics are true. So according to observer 1, there was a lightning strike in the front of the train. They waited, they drove an additional distance, and then sometime later there was a second event behind them. Observer number 2 saw 2 events at the same time, exactly happened at the same time. Both of these are correct, and in the real world, there is no God, right? Presumably there is no person overseeing this from above, so there is no absolute answer. In other words, if I am on a train moving forward, there were 2 lightning strikes. One happened in the front of the train, and then moments later, another one happened at the back of the train. If I wasn't moving, they both happened at the same time. These are both accurate and completely correct answers. So consequence number 1 is that simultaneity, or the fact that things happen simultaneously, is relative.
Wait, how would... Oh, it's a set time, so how would they be on?
Is it just based on like their
It's based entirely on your reference frame, which is exactly the
So
point.
if you were like, sorry. If you were like, oh, class starts later, then...
So the issue, of course, is that in the real world, we stick clocks on the wall that are all not moving relative to the Earth, and therefore they all are what we would call synchronized, right? However, if for some reason one of them was on a train moving, the time on that clock might not read the same as a clock that was stationary. And so this leads into the next consequence. The point, of course, is that it seems odd that we can take the perspective where we can actually say that it happened at simultaneity, right? That they happened at the same time. Because in the real world, you have no frame of reference where you can zoom far enough out to say, from the God view, this is what absolutely happened. There just isn't that possibility. And so therefore we must accept that it is possible to have 2 different perspectives and have both of those be right. All right. Consequence number 2 is called time dilation. Time dilation, hopefully the word dilation will be familiar to you because of your optometrist, right? What do they do in terms of... They put drops in your eyes, and what does that do to your eyes?
It makes your pupils bigger.
It makes your pupils expand. So we are talking about the expansion of time. And of course, the idea is if events are relative, right, which is consequence number 1, then perhaps time is relative. In order to illustrate this consequence, Einstein used a different thought example, not exactly a train, more like a space train or a space ship, right? Suppose that you have a fast, movable space ship of some kind that can move forward at some outrageous, ridiculous speed, right? We're going to set up a relatively simple timing device in order to measure time based on light, right? So what we're going to do is we're going to create we're going to create some sort of light source, right? Which we'll presume is a laser in today's terms, although Einstein was not familiar with a laser because it hadn't been invented yet. Then a mirror on the other side of the ship, and then some sort of receiver over here, right? photodiode in today's terms, but a sensor in most basic fundamental terms, right? The idea would be the light source and the timer and the sensor would be connected through some sort of timing device, right, which we'll just wire in our most basic circuit to a clock, right? The idea would be send a light ray across the ship, bounce it off the mirror, and back to the sensor. The timer would click off how long that takes, bada boom, time. Make sense? We can do this based on the fact that going across the ship would be a measurable distance, let's call it d. And so therefore, c, the speed of light, would be 2d divided by the change in time naught. We're adding the naught symbol because in this particular case, v naught is 0. So we're referring to this as the rest time, right? The time it takes for the light to travel across and back. And so what we're going to do is we're going to solve for delta t, right? So delta t in this case would be 2d divided by c. This is the time it takes for the light to travel across the ship and back, 2d, right? Divided by the speed. So that is the rest case, right? The rest case. But this ship is capable of moving at relativistic speeds like the fancy train from the first experiment. So if I redesign, where now I am moving at some outrageous v, right? Since light does not obey the relativity principle, while the light is moving across the ship, the mirror is moving that way because it's in the ship at some outrageous speed. And since the light is not obeying the relativity principle, if I were to aim the light at the mirror, by the time the light got across the ship, the mirror would no longer be there. Right? Does that make sense? Nicole?
What if the light was moving faster than the ship was? Would that affect it at all?
If the light was
Well,
moving faster than the ship? The light is moving faster
Yeah.
than the ship. The point is that the light does not add the speed of the ship to its motion, right?
Oh, and the
so you can
motion.
imagine that if we think about it in terms of vectors, the vector of the velocity of the light is this way, the vector of the train is this way. No matter how fast it's moving this way, over the time it takes to get across, the mirror is going to move no matter how fast the train is moving. Or
Is the mirror
ship.
like, when you mean like it moves, do you mean like it moves with the train?
Right.
But isn't the
But then the light moves with the train.
Yeah.
No, it doesn't.
Why?
The constancy of c does not obey the relativity principle. If I point the light this way, and then it leaves the light source, then it is moving this way while the train is moving that way. And because it doesn't obey the relativity principle, it does not move with the train, it moves independent. So we've only been thinking about it in terms of speed, but it is a vector. Velocity is a vector that includes both speed and direction. So not only does it not go the speed of the train, it doesn't move with the train in the general direction because it does not gain speed because there is no ether, right? But then the crazy thing is that if you're inside of the ship, you would see that the light went across and hit the mirror and came back, right? Because you'd be inside the ship, that'd be exactly what happened. Which means there's only one possible explanation. The possible explanation is that the light knew what was happening, and instead of aiming across the ship, it aimed for where the mirror would be.
What?
No.
Stop.
Absolutely. Because think about it, if you're inside the ship, when the light hits the mirror, you'll see the light hit the mirror, except that now the mirror's way over there. So that absolutely had to be what happened, is that the light knew what was going on and planned ahead.
That's like the thing
Or
that
light's
shines the
spinning
light
into
that
some
moves
It's
right
the
in
only
train.
possible explanation For the
That's
observed,
why I messed up.
right? If the observer is inside of the ship, if you are inside of the ship, thanks to relativity principle number 1, right? The physics that happens inside the inertial reference frame. If you set up a system where a laser hits a mirror and bounces into a sensor, whether or not you're stationary or moving really fast inside the ship, that's exactly what happens. So if you're not moving, the light hits the mirror and bounces up. If you are moving, the light hits the mirror and bounces up, except that during that time, the mirror has moved over here, and then during the time of coming back, the sensor has moved over here, and so it has moved over a much vaster distance.
So
you're telling me
the
this
light
light-
moves over that, like the
It
thing
does
that
not.
shines the light.
How does the
The
light?
things that shine the light have already shown it into space. So as the laser moves this way, the light that was shot has already left it. And as propagation goes, right, the wave of light is going to continue propagating straight forward in the direction that it was sent. And because it does not obey the relativity principle, it is not going to move horizontally during that time. So the only possible way for this to work out is that prior to the light leaving the light, the angle in which it is projected must be adjusted for the speed of the train.
Oh, by like a person?
No,
What?
by nature itself.
How?
We're going to get to it.
Is there something because it's in like in space because it's really fast? Like if you get in a car, like
So the reality is that in a car this actually does happen, but 300 million meters per second for the speed of light is so fast that it going across D is nearly instantaneous. So the only way we would get this exaggerated triangle is if we were moving near the speed of light, right? But this absolutely does happen under all conditions. And in fact, this is true for GPS satellites right now, because we shoot signals from towers on the Earth to space and back. During the time that the signal is traveling towards the satellite is moving. So the signal must be aimed where the satellite will be in order for this to work out. And then because of this effect, it has to be adjusted even a little bit more, right?
okay, but like if I was in a car and I like threw a ball at someone, it wouldn't like.
Yeah, that's
move,
what I
'cause
was
we're not,
thinking too.
like,
Right, because a ball obeys the relativity principle. When you are holding the ball in your hand, when you throw it up in the air, it is moving up and forward, right? Because the car is moving forward. When you throw light, it moves in only the direction that it is originally going and does not listen to the fact that the car is moving forward.
So by itself, it would come and then go like that.
Yes. This is the point, Cameron.
So, you're telling me, like, if I shine a flashlight and I'm moving, like, near the speed of light, like, that way, it will show up over there.
Right. All right, so the
How?
point then is if I measure, right, from here to here is D, right, which we already established as the width of the thing. And then from here to here, we're going to call it the travel length during that time, right? So it's going to travel L this way and D that way, which means that this, right, which is the hypotenuse of the triangle, is going to be the square root of L squared plus D squared. Right?
So it's
Makes sense? That's this Pythagorean theorem.
Yeah.
Yeah? All right, so that means, right, that the distance that this thing goes before it hits the light, right, is not 2D, right, but is instead 2 times the square root of D squared plus L squared, because the light actually travels along this path before hitting the sensor. Make sense? All right, so that gives us the speed of light as 2 times the square root of D squared plus L squared divided by what we're going to call delta T with no naught, indicating that this is a movement time frame, right? A time frame that occurs while moving at relativistic speeds. Hopefully, we recognize that if I just solve for delta T, right? Delta T is 2 times the square root of d squared plus L squared divided by c. What you'll see, of course, is that this is much less than that. Yeah? Because this is the square root of those things combined and is clearly the hypotenuse of the triangle, right? Which means that the time frame measured to go across the ship and back from outside perspective is longer than the time frame measured from the inside of the ship. Keeping in mind that if you were inside the ship and moving forward at a relativistic speed, you would still measure t naught, because in comparison to you, the whole system is not moving, right? Once you're in the ship, it just looks like everything is stationary. So if you are inside the ship, you would measure the time it takes for the light to go up and back to be a number, whatever it is, right? If you were outside the ship watching this happen, you would see the light hit the mirror and come back over a much longer distance and measure the time to be much, much longer. The point, of course, is that time has stretched, dilated apart due to the movement of the ship itself, right? Going back to this discussion, the relativity principle holds that reference frames, all laws of physics are absolutely true. So if I measure the time for the light to go up and bounce off the mirror and into the sensor and I get a number, that is correct. If I stand outside the ship and watch it happen and I get a number that is 10 times larger, that is also correct. And it depends on my frame of reference. And so, of course, the point is time is relative and not absolute. The reason why this all happens, right, is because time is not absolute. We think of time as marching forward at a very set interval, right, which we would think of as seconds and minutes and so forth. The point is that from the perspective inside the train, the ratio of seconds to minutes and so on is exactly correct. From the outside of the perspective of the train, the ratio of time is correct. But those two reference frames experience time, as in an individual second, as a different amount of time. In other words, the second is not a fixed amount of progression through time. It is instead a subjective based on frame of reference. And this is due, right, to the hypothesis that light determines time and not the other way around. Right? This is what we closed on yesterday. Okay, so there is some math that combines some algebra and some other stuff that basically ends up with a conclusion tying these two together, right? Where delta t is equal to delta t naught divided by the square root of 1 minus v squared over c squared. I'm not going to get into how I got all that because it's not relevant in terms of algebra. This is the relationship of the shift of time, right? In other words, delta t is greater than t naught when you divide by this decimal approximation. That if this speed is very, very slow, right? Very, very slow, like a car going 60 miles an hour. In comparison to 300 million squared, this ratio goes to essentially 0, right? 0.000000001. So that means 1 minus 0 gives you 1, the square root of 1. And so if you're moving at the speed of a car, the difference in time is basically nil, right? But the closer I get to c, the closer this gets to 1. The closer this gets to 1, the lower this gets, which means the square root of it gets much, much lower, which makes this get much, much, right? This value makes delta t get much, much bigger, right? So the faster I move, the greater shift in time, the greater dilation of time itself. This is why satellites, not only because of their distance away from the planet, but also from the fact that they are orbiting at thousands of miles an hour, are moving fast enough that the relativistic speeds must be taken into account. So when they program GPS to measure where you are on Earth, right? This is a positioning item, just like positioning where the sensor of this is. They have to consider that, or else if you're moving, you'll be in the wrong spot, right? So you can imagine that a car moving forward at 60 miles an hour, if the satellite does not adjust for the fact that the satellite itself is moving at thousands of miles an hour, it can be off by seconds. Well, seconds doesn't seem like a lot, except that in a car going 60 miles an hour, seconds is a lot, a huge amount of distance, right? That's the difference between stopping before the intersection and blowing through the intersection, right? So these things have to be accounted for in the real world. Lila.
Is this idea of like time being a relative variable kind of like how like in sci-fi movies, like going through the space-time continuum, that sort of thing?
Yep, it's what inversely happens as a result of time dilation, which is called length contraction. Length contraction. All right, so first is planet A, planet B, with a new rocket ship flying from planet A to planet B, right? Moving at some speed, v. A relativistic speed, very fast, right? We are going to say that from A to B is what we would call our rest length, because from this point of view and looking at it, A and B are not moving. Make sense? All right. So the time from A to B, right, over this distance L naught would be our relativistic time because we are moving, right? So delta T equals L naught divided by V, which of course is just your V equals D over T rearranged. Solve for T. So if we solve it for L naught, which is the length discussion here, L naught is V times your delta T term. This is described as the rest length. Interesting that the rest length is measured by the relativistic time. Right? This is because we are measuring while moving. Vice versa, let's say that we're going, A to B by parking the stationary rocket and moving the universe, right? Totally possible in terms of relativity, right? Is to have A move this way at V and have B move this way at V. Now, the distance from here to here is our relativistic length, right? Relativistically moving, yeah?
Are they moving at the same speed?
Yes.
Okay.
Although my arrows are not the same length, I apologize. In this case, length is determined by V times your rest time, because you are not moving. All right, so L is V times delta T times the square root of 1 minus V squared over C squared, by just introducing the combination of T naught from the previous equation. Well, L over here is V times delta T. L over here is V times delta T times this additional term, right? Which under most conditions is hopefully just 1, right? With 0, 1, making the two lengths the same. But when V is very fast, this becomes a decimal, right? And since we're multiplying instead of dividing in this case, this makes the length much shorter, which is a way of thinking of the fact that the ship is actually much bigger because it did not take near as long to get across this distance. So what happened is that due to moving at relativistic speeds, time stretched out. But as a consequence of time stretching out, the space between points is now shorter, which is how we can account for some of the thoughts, right? If it takes longer, but it is a shorter distance, then we can accomplish the same speed. And that's the point. The speed being the speed of light. The speed of light determines how time and space adjust through movement. So, what Einstein concluded was what an object loses in length, it gains in time, or vice versa. Right? Einstein called this four-dimensional space-time. And what we mean by that is that the fabric of our universe is comprised of 4 dimensions that we navigate, right? 3 dimensions of space, X, Y, and Z, right? Up, down, front to back, and the other one, right? And 1 dimension of time. And the point of this entire thought experiment, right, with these 3 consequences, is that if I change space, I can change time. And I do that change simply by moving at fast speeds. So moving through the universe has an effect on the dimensions of the universe. And time itself is not a fixed universal, but is instead embedded in the fabric of the universe itself. This is the idea that spawned all sci-fi movies in terms of time travel. If you move at a relativistic speed, the time for you, right, is your dilated time. So if you move at the speed of light, right, which goes back to what would I do, what would I see if I rode a light wave, time itself would not exist because time does not progress. Because you have taken space and condensed it so small that time itself has stopped, right? So that's the idea, or stretched it out.
Wasn't there like a room that was dark or something?
I don't know.
I read
don't
this a really
remember.
long time ago.
I don't remember.
Wait, well, what happens if you're in the loop and then you go out of the loop and nothing's changed?
So if you step between spaces, right, then you change your relativistic speed, right? And then you would go and experience whatever is happening in that other inertial reference frame.
But you wouldn't change even though you had changed. You wouldn't change back.
No, correct.
Left.
Yes.
Yeah.
One of the most realistic representations based on fiction is the Flash, right? When the Flash runs really fast, the reason why he can manipulate things around him is everything slows down, right? Everything around him slows down. That's because he's moving so fast. The paradox that was discussed as a consequence of this is called the twin paradox. This is actually kind of relevant because the twins just finished their NASA experience, right? And we talked about that on the screen the one day. The twin paradox is the idea that if I had 2 twins, right, and one of them got the short straw, he has to stay on Earth, right? The other guy gets in a ship.
Goes to Mars.
He's going to go a lot farther than Mars, traveling at near the speed of light. So he's going to travel at relativistic speeds in a direction away from Earth, right? At extremely high speeds, time is going to run very slowly for him within his reference frame. So if he travels for what the guy on Earth experiences as 40 years, right? And then turns around and comes back at the same speed, he gets out of the ship, he is now 21, where his buddy is 61 because time slowed down
Is
for
that like the
him.
actual number?
Depending on how
Once you
fast he's
come
moving.
back to
So what's
Earth-
amazing, right, is that if he moved at the speed of light, he would come back and he would not have aged at all.
Once you come back to Earth, would you immediately start aging
Yes.
in a rapid pace?
No.
No?
At the continued normal pace of the speed around you. Because what you have to imagine, right, is if you go back and think about your fundamental forces. Electromagnetism is the thing that holds our molecules together, which means that time, right, for you, your lifetime, is governed by the speed of light moving molecules around within your body, right? So if the speed of light affects time, if you are under relativistic speeds, then the entire function of how the electrons are moving in your body is changing according to this shift, right? So your heartbeat is on the same pace with a clock that it would be in any other reference frame. It's just that in comparison to the two reference frames, time runs slower, right? So if you were the lucky twin and you got to go on the ship, when you got back, your brother would be super duper old and you would be super duper young, right?
So, but then you wouldn't catch up to the age you were when you left on Earth, so technically, like,
So
that
now,
brother could live another 60 years, and
Exactly.
his twin would be long dead.
Why
exactly,
don't you want to do that?
exactly.
Wait, so you...
Cameron,
Okay, so in the Flash, if he runs fast enough, he goes back in time. So if you run faster than the speed of light, do you go back?
so this is the thing, is that is going back in time, right? Is if you pause growing and everyone else continues forward, you go back to the future. That's why it's called Back to the Future.
Oh!
It's pizza time.
Right?